All right, so let's just go through how you do the goodness of fit tests on program mark real fast. So you want to choose the most general model, in this case VT, PT. Click on that little icon to make sure that's retrieved. And then we're going to come over to tests. And first we'll do the bootstrap goodness of fit. And we're going to output all of the output variables that they suggest. It then ask you where do you want to store the output from these simulations. We'll just stick with bootstrap results.dbf, say OK. And now I'm just going to run 50 simulations. You probably ought to run 100 just because I don't want to be sitting here all day. And then click OK, and it's going to start doing these simulations. So it's taking the number of individuals in the original data set, and then for the parameter values that were estimated, it is generating 50 simulated data sets based on those parameter estimates with you know, exact fit to the assumptions of the Cormack-Jolly-Sieber model. So the deviances and the c-hat values that we get from the simulated data should not be contaminated by any lack of fit issues. And so we can compare the output from these bootstrap results to the actual output that we got. And one thing to look at is for the actual model, we had a deviance of 36.40. Okay, and the other thing that's good to know from the actual data is the c-hat that was estimated. And in this case, if we look at the full output from program mark and come partway down, you could just search for c-hat. It gives you the estimated c-hat, and that is the deviance that we just looked at divided by the deviance degrees of freedom, which would refer to the number of different capture histories in the data set. Okay, so those two values are the values from the actual data, and then what we'll want to do is compare those to the simulation. So we click on simulations and then click on view simulation results, choose bootstrap results, obviously, because that's what we just ran. And here's the output from all of those simulated data sets. It ran the analysis and calculated all the parameter estimates and so on. And here's a number of parameters. So in each case, it correctly got the number of parameters right. This is the deviance from each of those simulated data sets, the deviance degrees of freedom. You divide the deviance by the deviance degrees of freedom, and that'll give you your c-hat estimate for the data set. Okay. And one thing that they mention in the Mark book is, one thing you can do to kind of look at where the actual data compared to these simulated data is to order or to sort the simulated data by deviance, and then come down here and see where the actual deviance from the real data come out relative to the simulated data. And our deviance from the real data is 36.4, and that's down here. Here's 36.1, here's 36.8. So we're getting pretty close to, this is the 50th highest, 49th, 48, 47, 46. So there are 1, 2, 3, 4, 5 deviances greater than the actual deviance from the data. No, actually 4. 1, 2, 3, 4. So, this is 50. So if we double that to 100, that's about 8 values that are greater. So gives us a p-value, if you will, of 0.08. You might say, okay, it's not less than 0.05, so we're good. But, that's pretty darn close. So you might want to be a little cautious there. So now how do we get our estimates of C hat that we might use for adjusting the AIC values? Well, as they talk about, there's two ways to do this. You can use it based on the mean of the C hats from these simulations and based on the mean of, the deviance from the simulations and the C hats from the simulations. I know that our actual value is 36.4. So if I divide 36.4 by 25.86, I get 1.41. Okay. So, a little bit above 1, maybe not too bad. How about if we look at the actual C hat from our data, which was 5.2, and we divide that by 3.477. That gives us 1.49, so a little bit bigger. And as they say, um, probably best to err on the side of caution, go with a bigger C hat value. Um, so let's go now to the third approach to estimating C hat, and that is the median C hat, which they explain in the Mark book. They also mention it's probably good to change the upper bound if it makes it greater than 3 to just set it to 3, because any C hat value greater than 3, you've got real problems you need to think about with the data. And then the next cell down is the number of intermediate points between the lower and upper bound. I'm going to decrease this. I'll make it 6. So that means in addition to running simulations for when the deviance is 1 and when the deviance is 3, we'll run 6 more simulations with equal cuts between 1 and 3. Okay, and then this is the number of replicates at each point. You probably want this to be a little bit bigger. I'm going to set it at 20. And then I'm also going to output it to an Excel spreadsheet so we can just see what's happening with these data. So now it's saying, okay, I'm assuming that the C hat over dispersion parameter is 1, and I'm simulating, a bunch of data, in this case 50 sets of data, and then running, getting the deviance in the C hat. And then I do that for another cut point, and another cut point, and another cut point. So for 8 different values of C hat, we're running these 20 different simulations, so 160 of them. So you can see that this could take a while. And then what we want to do is look and see how those values of C hat compare to our actual value of C hat that we got from the real data. So first thing is the estimated C hat that we get from running the regression through all of these simulated data that we've got is 1.52, so a little bit bigger than the other estimates, but all right in the in the same ballpark. Okay, and if we close out of that, we'll see the logistic regression that it has fit to the simulated output, okay? And these red dots are the proportion of these 20 simulations for C hat of 1 where the observed deviance was less than the actual deviance of 5.2 from the data. So if we look at the output, and maybe I'll zoom in on this, or I'll make oops, I didn't mean to do that. I'm just going to move this over. I'm going to make the fonts bigger so you can see what's happening here. So here's the simulated C, and then these are all the result C hats that you got from each of the 20 iterations. Yeah. And now what we want to do is find out how many of these are less than the observed value of 5.2 that we got from the actual data. And so I'm going to use the count if function in Excel. And you don't need to do this. I'm just kind of hoping this maybe makes this a little more transparent about what's happening. And then I want to see how many of those are less than the value that we actually got, which was 5.20 something something. Okay, and then I'm going to do this for some of the other simulated data. So I'm going to hit F4 so that that is a absolute reference. And I hit it, and it's like, oh, yeah, all 20 of these values are less than the observed deviance C hat of 5.2. And again, if we look at that, that's where this 1.0 comes from, saying that 100% of the C hat values from our simulations were less than 5.2. So let's go back to our spreadsheet and look at it for the next values. So Control C, I'm going to copy this, and I'm going to go for this next cutoff, which ends right here. Okay, and then Control V, and now it's saying 13 of these values are less than it. So, you see this one is greater, that one's greater, and so on. And if we look at the value here, yeah, that's 65%. Okay, and then we get down to 45%. So somewhere between 1.28 and 1.57 is where it flips from 50% being below that observed value of 5.2 to more of those values being above 5.2. Okay, and what Mark is doing is it's fitting a logistic curve to that. Doesn't really look like it here. We don't have a lot of cut points and a lot of data, but what we're using then is we're saying where where is the 50% point of the logistic regression, and that's going to be our best estimate of the value of C hat. And you come down here, and it does seem to be somewhere around 5.2. Okay, so that's just sort of an explanation of the where that logistic regression is coming from. And now, since we're finding that C hat is probably not actually equal to 1, we're going to do an adjustment. And notice how these models are arrayed here in our delta AICs going from 0 to about 13.8. So I'm going to change the value of C hat from 1 to 1.52. And what that does is it means now that instead of using the AIC value, we're using the QAIC. And that changes our delta AIC values. And you'll see that the weight for this top model is now much, much higher than it was. So here it's 97%. So, you'd say that, hey, that's the best model. We don't need to look at any others. If we go back and make this at 1, now, well, it drops to 96%, still says that's got by far the most weight. But as I talk about in the book, the weight of the more complex models with more parameters is going to drop when you use this QAC value. So if I were to adjust it and put it to, say, 2, now, yeah, and now it's like 98% on this top one. So these models with fewer parameters are going to get more of the weight. So that's basically what this is all about, is to adjust the ranking and weight of those models, because we know that the data aren't really fitting the assumptions of the model completely. So we want to be more careful in terms of looking at our output.